You are most I want to thank you. But before we start, allow me to invite Idiofe girls to lead us in an opening prayer. Idiofe girls, get for us one girl to lead us in an opening prayer.
Hello.
Yes, hello.
Hello.
Yes, hello, you can go on. Idiofe girls, we are waiting for...
Let us pray. In the name of the Father, and Son, and the Holy Spirit. Amen. God Almighty Father, we thank you for the gift of life. We thank you for the gift of everything you've given to us. And above all, we thank you for the gift of this day. Above all, we pray that may you send your Holy Spirit upon our facilitator, so that you may be able to deliver for us what he has prepared for us. And we also pray for all the students that we are going to, as we are attending this seminar, we may be able to understand whatever they are going to deliver for us and retain it in our memory, that we may be able to remember during our examination. For this we pray to the Lord. Lord, hear us.
Amen.
In the name, the Father, and Son, and the Holy Spirit.
Okay, thank you so much, Idiofe girls. We want to welcome all the schools that are joining in from the different parts of the country. You are most welcome. We want to thank all the teachers that are joining in, that have connected their students. We are really very grateful, and thank you so much for joining this session. We are really very happy, and thank you so much for joining. We are here for chemistry, and like our invitation was very clear, we are going to deal with mainly paper 3, and then we shall also talk about paper 2 and then paper 1. Our facilitator is already on the call, but before we start, allow me to invite the principal at the Ministry of Education and Sports, Mr. Ronald. I don't know whether you can be able to unmute and greet us. Okay. So allow me now to invite our facilitator, Teacher Eva, to lead us in the discussion. Teacher Eva, you're most welcome. Teacher Eva?
Good evening, everyone. I'll start by introducing myself. My name is Eva Kabayonga, and I am a teacher of chemistry. I want to welcome you all to this short interaction that we are going to have to see how best we can improve our performance in chemistry. I'll turn off the video so that we proceed. But I would like to request someone to lead us in a word of prayer. Can I have a volunteer raise their hand so that they are unmuted to lead us in a word of prayer? Oh, I've been told you have prayed. Okay, I'm really sorry for that. So I'll start straight away. I'll be taking you through this session with a colleague of mine, but I'm going to make just very brief remarks on the theory paper of chemistry. We all know that chemistry has 2 papers. Chemistry paper 1, which is just 50 objective questions, and then also chemistry paper 2, which includes 10 structured questions, giving a total of 50 marks, and 4 essay questions, from which a student is supposed to choose 2. In that section, a student gets a total of 30 marks. So the whole paper is out of 80. I'm going to just mention very little about the theory paper because I know HELP has managed to provide several sessions in which the students and the teachers have discussed and shared on best practices that will enable a learner to excel in chemistry paper 2. So I'm just going to mention some briefly, but much of our talk today shall be on practical. Now, chemistry paper 2, many a times students do not get their full marks because of not presenting their work well. So we should always watch out how we write our answers because the person marking you does not know that you know. So you have to write so that they clearly understand that you know. So I'll just share this slide quickly, which is showing some of the areas we should look at. In section B, where they tell us to choose only 2 questions, please do not waste time doing many more other questions because they'll not be marked. The first 2 to be, the first 2 that you put on your answer sheet are the only ones going to be marked. Then all working should be clearly shown. Some candidates miss marks because they are just using words which have arrows or equal signs, which have many meanings in chemistry. Can we be careful? Sometimes you find a student writing 40 grams of carbon and then putting an arrow and then putting 5 grams of carbon dioxide. What does that mean? Can you write the words that 40 grams of carbon produce 5 grams of carbon dioxide? That way you're going to get the marks because in most cases, students who use the arrows actually know what they are writing, but they are using a shorthand which the examiner does not know. And so the examiner is not going to give you marks. So let's be careful about that. Then I have seen many students, because when we were teaching you how to write equations, we taught you how to write the word equation. Then you write the equation before balancing it, and then you balance it and write the final one. In the exam, can we make sure that we present only one equation? Here, we are not expected to show the working. Write the final equation. If you want, you can work it out elsewhere, and then you come here and show the working. Okay? When we are writing answers, if they tell us, name one allotrope of carbon, the question has asked you for only one, and yet for you, you know 2 names. So you feel you want to write diamond, you want to write graphite. Good. They are not going to give you extra marks for having written the extra one. Since they asked for 1, they'll give you only 1. However, you risk, if the excess one that you have written is wrong, you are going to miss the mark even on the correct one. So my advice to you, dear students everywhere, when they ask you for 1 thing in chemistry, give 1. When they ask you for 5 things, give 5 things. Do not waste time giving excess because it does not impress the person marking you. Okay? Then, when they tell us to draw,
my advice to you is draw using a pencil, because it is very easy to erase a mistake when you draw with a pencil, but it is not easy to erase it in ink. So those apparatus of the laboratory preparation of gases, let's draw them in pencil. The diagrams for bonding, whatever we are drawing, let it be in pencil. Although here I have to warn you, no one is going to subtract marks if you draw in ink. But it is dangerous because many times you cannot erase a mistake, and so you end up sending forward very untidy work. Calculations, I said I'm just going to speak very few things because I know HELP has handled the chemistry theory paper. When it comes to calculations, I know, my dear students all over the country, you have practiced on calculations and you're very good. I have said, let us show all the working so that a person can follow what we are doing. But now a common area where students miss marks is, for example, you have calculated and your answer, let us look at this question I have given here. It is saying calculate the mass of silver chloride that will be precipitated if excess silver nitrate solution is added to an aqueous solution containing 2.56 grams of sodium chloride. Many students will manage this. Then you find that when you now press the calculator to get the final answer, you are getting maybe 9.768321. Some very long number is the one appearing in your calculator, which means you are expected to round off. But now the question is, to how many decimal places will you round off? So when you are rounding off, therefore, you will go back to the stem of the question where the question was, and you look through. What was the accuracy in the question? How many decimal places were provided in the data that is in the question? If you look at this one, there is this figure 2.56. That is to 2 decimal places. So which means the person who set the question wants you to use that accuracy. So you go now to this long figure in your calculator and you round it off to 2 decimal places. Here I'll make a disclaimer. Sometimes you look at past paper questions and you find that in the stem of the question, they have used numbers with different decimal places. They could tell you 5.0 grams of silver chloride react with 2.56 grams of sodium chloride. So there is a number there which is to 1 decimal place. Then there is also a number which is to 2 decimal places. So the question is, what do I do as a student? You are free to round off to any of those, which is in the stem. The marking guide will cater for that. So always, after you have worked off, before you round off, go back and check how many decimal places there were in the question, and that should guide you on the very final answer. I do not have to tell you that you always also have to check and put the units. Many students miss marks because they don't write the units, especially on the final answer. If I've told you to calculate the mass, the standard unit for mass in chemistry is grams. So indicate the G at the end of your figure. Then the other point I will talk about, you have learned formulae and symbols, and many students get to the exam thinking that they have to write these formulae many times and so on. Word of caution. You are only going to use these formulae and symbols when you are writing equations or when they ask you that write the formula of this. Those are the only places in chemistry paper 2 where you are expected to use the formulae and the symbols you know. Otherwise, throughout the chemistry paper, you are expected to use the names of the substances. So practice those names: copper 2 sulfate, copper 2 oxide, zinc hydroxide, and that kind of thing. Even when you draw a diagram, when you are labeling the apparatus on the diagram, make it a point to see that that apparatus, if there is any chemical there, it is labeled with the name, not the formula. You will miss the marks. Even if you're describing preparation of a substance, let's say preparation of lead 2 sulfate, which is an insoluble salt, you're expected to mention, maybe get 2 centimeters cubed of lead 2 nitrate solution, the words. The moment you write the formula, they will stop marking. Okay, you lose marks, and that whole description, even if it is correct, it does not get marks. Then, because I have said you're going to write the names, I want to emphasize that in chemistry exam, you are expected to write chemical names because you're chemical students, not what we call trivial names. So instead of calling something lime water, what is its chemical name? It is calcium hydroxide solution. Notice that its name is even telling you the state in which it exists. Many students forget to specify that state or condition of the reagents, and they miss marks. When you are talking about using an acid, for example, here I've shown dilute sulfuric acid. Do not just call it sulfuric acid. Well, you can call it sulfuric acid if you're not sure. Because if you're not sure, you can get some half mark. But if you are sure that in that reaction they use dilute sulfuric acid, write dilute sulfuric acid so that you get the full marks. If in another reaction they use concentrated sulfuric acid, write it. For the salts, many of the salts that we use, of course, we know they can exist in the solid state and also in the aqueous state. So do not just tell someone that the reagent is barium sulfate. They'll wonder, which barium sulfate? Is it the solid or is it the aqueous solution? So in order to be very clear and get maximum marks, you should mention barium sulfate solution, anhydrous copper 2 sulfate, hydrated copper 2 sulfate, copper 2 sulfate solution. And then the other things which I can talk about, many times these days, the chemistry questions are linked. In part A, they tell you, state what was observed. Then in part B, they tell you, explain the observation above. Please take time to notice those. Which observation am I explaining? They even point the observation in B above. So go to B, check what you had written, and that is what you explain. Another thing I can talk about, when they ask you to write observations, what are you supposed to write? In chemistry, observations are about what you have seen, what you have smelt, or what you have heard. But the most common is what you see. And what we see, because chemical changes are about forming new substances, usually the new substances look very different from the original ones. So when we write what we have seen, we should mention how the first one looked and how the final one looked. For example, something like the white solid turned to a black solid. And a colorless liquid was formed on the cool parts of the test tube. There, a person can visualize everything. Please, we must mention both the color and the state to get full marks, because there are times when the marking insists that you must tell us the color and the state. White precipitate, not just precipitate. Blue solid. So can you take time and revise those observations so that you get them right? The last thing I'm going to share with you, just for emphasis, is that when you are told to explain anything in chemistry, anything you're explaining, you're actually narrating the equation. So in explaining, make sure you write also the chemical equation. Write the chemical equation and then say it in words. What do I mean? If you are told that when sodium hydroxide solution is added to a solution of copper 2 chloride, a blue precipitate is formed. Explain. You are going to write the equation of reaction showing sodium hydroxide reacting with copper 2 chloride to form copper 2 hydroxide and sodium chloride. Now, of the products, the sodium chloride is not important because it did not make any unique observation. But the copper 2 hydroxide is important. It formed a precipitate. So when you are now, after writing the equation, the explanation will simply be, the reason for that is that sodium hydroxide reacts with copper 2 chloride to form insoluble copper 2 hydroxide, which is the blue precipitate. So those are just some of the tips I can talk about in chemistry paper 2. I want to hand over to my colleague. I don't know if she's already online, so that we share more on the practicals. Otherwise, you will ask questions later on.
Teacher Eva, I think we may need to pass through for her. I don't know that she's using other names. Yes, BS.
Yes, good afternoon, everyone.
Good afternoon to you.
I'm happy to be part of this discussion. So we'll be talking about the chemistry practical, Kidabwa, Silver, and Kwereka, abbreviated there as BS, but I'm glad to join Teacher Eva as we go through the discussion of the practicals today. As we all know, the practical has 2 questions, and the 2 questions are, number 1, where you expect to be looking at volumetric analysis. If you don't have volumetric analysis, then you're looking at
Hold on a little bit. Let's sort something small.
I hope you can hear me. So we said we'll be looking at good. The chemistry practical, where we have 2 questions. One question is supposed to be volumetric analysis. Then the second question is qualitative analysis. Now we can have a titration. If we have a titration, we'll expect things that you're supposed to be using. Either you're using a pipette. And when you're using a pipette, you must be in position to record the pipette volume. Recording the pipette volume, we are supposed to record it according to 1 decimal place, assuming that your pipette capacity, many times when you receive a pipette, it has something like that. Now, in this pipette, they will write a figure, either 25, some of them can be 20, but of course they don't appear together. So it depends on your capacity. Now, when I see this on my pipette, there is also something here, which we call a meniscus. So if they say pipette 25, that means I should not exceed this line here. I should not be below or I should not be above that line. That is what it means that I have now pipetted 25. Meaning that if I'm above that line, I've exceeded 25. If I'm below that line, I am below 25. Remember, a pipette measures accurately. So if they say 25, make sure you have your meniscus on that line. Then, on your paper, they will write for you volume .
Teacher Eva, we have lost the volume. Teacher Eva, we have lost the volume. Teacher Eva, kindly have your microphone on, Teacher Eva. Teacher Eva, kindly let's have your microphone on. Teacher Silver. Teacher Silver.
Sorry about that. I could probably repeat a bit of this. I talked about the apparatus that we use when we are doing a practical that we are calling a titration, or where we have volumetric analysis. We use a pipette, we use a burette. When you're using a pipette, it has a capacity. There are those of 25, and then there are those of 20. At all levels, they are the most common ones. The question would say pipette 25 or pipette 20. So that means you have to look at your pipette and find out what is the volume of my pipette. If it is 25, I have just said, usually the apparatus have meals, but 1 meal is equivalent to 1 centimeter cubed. So that means I have 25. When they tell me to record the volume of pipette used, we should record to 1 decimal place. That is the most acceptable. But they also accept if someone writes 25. Then I talked about a burette. When you're using a burette, it has a scale. It starts from 0, moving downwards. So that means 1 should be there, 2, and the last figure here is supposed to be 50. Now, if this is what you're looking at, you're supposed to read how much have I used and then record that in the table. I'm sure we have looked at that table, given that we are doing the final exam in a few months. We must have filled that table before. So if I'm looking at this, assuming that is where I have stopped, I have to record my burette volume. We read moving downwards. That is why I said you have 0, 1, 2, 3, up to when you get to 50. Now, if you're filling the table, these marks are very good marks because you're just doing something that you can record and get all the 7 marks. You have what we call initial burette reading. Then we have final burette reading. And then here we have volume used. I'm not going to put something, but many times they will ask you volume of BA1 or volume of BA2 used. Now, what is initial burette reading? Before I start my experiment, that is what they call the initial burette reading. When we are filling this table, it must be filled to 2 decimal places. Now, assuming I first filled my burette and it is at 0, my initial is going to be 0.02. That is what I talked about as 2 decimal places. Meaning if someone just writes 0.0, they will not get any marks for that bit. Please take note, when we are filling the table, it should be 2 decimal places. So initial is before I start. Now when I start my experiment and I'm shaking the color, I have stopped somewhere here. That is what I'm going to read, and I will write as my final burette reading. So assuming I have stopped at 15, if I write 15, I'm not getting any marks for that table. 2 decimal places. So it means you're writing 15.00. Then how do you get the volume of the substance used? For you to get the volume, you need to subtract the initial from the final. So in this case, I have 15 minus 0, 0, and that would give me 15. That is the volume used. This whole table usually has 3 columns. That means you repeat the experiment 3 times. Now, the reason of repeating it 3 times is to get what we call consistent. The reason you're repeating this 3 times is to make sure that you get results which we call consistent. Consistent means they are close to one another. If the first one was 15, I should be more careful when I'm doing the second one. So assuming I have decided to refill my burette, you can decide to do that, but the solutions are not usually enough. So instead of refilling, you can decide that I'll start at 15 again. What does consistency mean? I should end and get a figure that is close to 15. So assuming I end at 29.8 0. I need to subtract the 2 to get the volume used. And of course, when you subtract the 2, that would give you 14.80. That is what you get. If you look at these two figures, 15 and 14.8, the two figures are close. They have a difference. When I subtract them, the difference is 0.2. Now, this is also not very good. For consistent results, we talk about a difference of plus or minus 0.1, meaning I can have exactly 15 for the first one. Even the second one, I get 15, or I can have 15.1 or 14.9. Those results would be consistent. I said this table has 7.5 marks. These are marks that you can get as long as you fill all the figures to 2 decimal places and make proper subtraction. We say the subtraction happens for you to get the volume used. Initial is before I start. Final, when the color changes, and then when I subtract the 2, I get the volume used. So that is about filling this table and being able to get all your 7 marks. Now, after filling this table, they will ask you to get the volume, average volume used. Because you have done it 3 times, you can decide to use all your 3 figures. So assuming I had 15.00 and another one is 15.10, I can choose 2 and divide them to get the average used. That means I'll have 15.05, and these are centimeters cubed. Someone can say, I'll use all my 3 figures, assuming the next figure was 14.9. You still divide and get your average volume used, because the volume that you're going to get here is the volume that you'll be using for your different calculations. That is getting the average volume. Now, before getting to the average volume, there is what they call volumes used to calculate the average. You get them from the table, meaning that if they were not in your table and you have looked at your neighbor, you will not get marks for those figures. So you look at your table and pick the volumes used and write them here. After writing them, you work out the average, like I have said here. You can use 2 of them, you can use all the 3, but ensure that your results are consistent. Now, after doing this, there's what we call accuracy. We are going to give you marks according to what we expected. Now, usually, the practical, your teachers do the practical and they send a figure to the UNEB examiners to look at. But when they went through the experiment that the students were given, they got, assuming they got 15.00. That is what your teacher handed in. Now, if that is what your teacher handed in, you will be awarded marks here for being accurate in comparison to this. If you are getting 15.00, in this case, you'll get all the 3 marks because this is close to what your teacher handed in. Now, assuming for you have 16.00, 16 is too high from what we expected. And because it is too high from what we expected, you're not going to get any marks for being accurate. So what can I emphasize here? When they say pipette 25, make sure it is 25. Titrate, as soon as your color changes, make sure you are recording, such that you don't overshoot, neither should you undershoot, in order for you to get these marks here for being accurate. So I think that is something about the table. And these are marks everyone can get because you're not yet into calculations. You're only following the instructions. And as you follow the instructions, you fill the table. After filling the table, you get your figures to calculate the average. Then from there, you do the average. And then for us, we compare. This is what the teacher gave us. What did this student get? Of course, there's a range to this. They will mark students from plus or minus 0.1 up to someone who will get plus or minus 0.5. But of course, the marks differ. This one who is most accurate will get all the marks because they are accurate as the teacher expected. Now, those ones who will get 0.2 as their difference from this that was expected, their marks will keep on reducing. So for example, if someone has a difference of 0.2, they might get only 2. Then the one of 0.5 as their difference will receive a half, meaning that you're losing marks if you're not accurate. So I hope we shall work on being accurate at that point. Now, after that, you have filled the table. What you'll expect is what teacher Eva kept on emphasizing. They can tell you, write an equation for the reaction. Now, in what they have given you, for example, they can say sodium hydroxide, and you're reacting it with hydrochloric acid. Pipette so much of sodium hydroxide, titrate with hydrochloric acid. Then after that, you fill the table and done all that, they'll say, write an equation. What am I emphasizing there? Practice writing the equations. There are not very many that we write in the practical. It is usually acid-base or an acid reacting with a carbonate. So you can practice those equations because from the equation, you're expected to get a mole ratio. And when you get the mole ratio, you use that to do the other calculations that can come along with what is expected. So practice writing equations as you prepare for the practical because it is something that you might be required to do. Sometimes we have questions where they have given us mole ratio, depending on what has been said. But if it is not given, please take note that you're in position to write an equation, which takes you back to the procedure. Pipette 25 of sodium carbonate, add 3 drops of phenolphthalein indicator, then titrate with sulfuric acid. So when they say write an equation, you know it is between sodium carbonate and sulfuric acid to give you the expected products. So we need to practice writing equations. The other one is calculations. These ones will vary. I know you did this under mole concept. Please take note. They can tell you to determine molarity. Maybe they have given you the one for the acid and they want the one for the alkali. Or they have given the alkali and they want the acid. So look at molarity. How do we calculate questions of molarity? Number 2, they can ask you about concentration in grams per liter of one of the solutions that you're using. And these are questions that you did under mole concept. So I'm only reminding us that we need to visit. When you're preparing for the practical, you need to look at all these calculations. How do you calculate molarity? How do you calculate concentration in grams per liter? How do you calculate RFM of a compound that you have given me as unknown? They can say X carbonate. Then they tell you find the RFM. You need to know how we do that. Where there is RFM, sometimes they can also ask for relative atomic number. For example, they say, what is the relative atomic number of X? All this comes from the calculations. Now, these cannot be free marks. That is why I'm talking about practice and practice and practice. The more you do the calculations, they become part of you and you can pass them. We can be required to find water of crystallization. I can write a formula here. So assuming they tell you you have an acid whose formula is that, then they put N and water. They tell you, find the value of A. You're looking at water of crystallization. All this is part of mole concept. So can we take our time and practice? I know you need the marks. When you pass the practical, already you are at a higher standard of getting a very good grade from chemistry. So you need to do some practice on this. Of course, we don't have a lot of time. I will talk about the other expected number, 1. If you don't get a titration, what can you get? We can get rates of reactions. This is also one of the topics that we have covered. Sorry about that interruption, but we'll continue. I said the next question that you can expect is rates of reaction. Now, rates of reaction, we define rate of a chemical reaction as time taken for you to get a certain amount of product. So we have amount of product formed over the time taken. How long has it taken for me to get a certain amount of the product? If you don't do that, it could be amount of reactants used up. So you can measure the rate of reaction either by looking at how much product am I getting or how much the reactants have been used up. And then you consider the aspect of time, because there is no rate why you don't have time. A reaction between sodium reacting with chlorine to get sodium chloride. I'm just giving this as an example. It is not something that we usually do practically when you're looking at rates of reaction. I'm just using it to explain. I can consider one of these reactants. I say, I am starting with 10 grams of sodium. How long does it take for all these 10 grams of sodium to completely react? That is considering the reactants. Someone else can consider the product, which is sodium chloride, and you want to find out how long does it take for me to get maybe 15 grams of sodium. That is looking at the rate of reaction. Now, I'm sure that when you did rates of reaction, you looked at factors that affect the rate of reaction. This is something that is examined practically, but as well as theoretically. Now, some of the factors that we know is temperature. The other factor is concentration. Concentration of the reactants that I am using for my reaction to happen. I'll talk about these two, but there are other factors like surface area, pressure, and so on. I'm talking about these two because they are the ones that we examine practically. So, temperature. How does the rate of a given reaction vary with change in temperature? Or how does the rate of the reaction vary with the concentration of the reactants. Now, these reactions usually happen between many compounds, but I can talk about one or two. For example, we have magnesium reacting with any acid of your choice. I'm using sulfuric acid to get magnesium sulfate and hydrogen. Of course, we write the states. Now, in this practical, if I want to deal with temperature, I'll use the same mass of magnesium. I'm sure we know what we call the magnesium ribbon. I can say measure 2 centimeters cubed. No, these are not just 2 centimeters of the magnesium ribbon. And then you keep putting that ribbon in a conical flask containing the acid. So you add the ribbon. And then you should also have a stop clock that you're using. How much time does it take for the ribbon to disappear? Because when I add the ribbon to the acid, it will dissolve. When you add magnesium ribbon to sulfuric acid, it dissolves, giving you the salt and then the hydrogen. Now, if I want to look at any factor, I can do it. For example, I will tell you, keep warming the acid to get a certain temperature. So you start with room temperature, which you record according to where you are. You could be in a cold place or you could be in a warm place. So you record your room temperature, depending on where you are. So we are assuming maybe the room temperature is 25 degrees Celsius. So you do the experiment and note how much time does it take for the magnesium ribbon to dissolve and completely disappear. So in this practical, you usually have the aspect of time. So we put here the time taken, and then here we put temperature. If what I'm looking at is temperature. So at 25, which is room temperature, how many minutes did I take? Maybe I took 40 minutes. I repeat the same procedure, but this time taking a temperature of 30, taking a temperature of 40, 50, and so on. In all this, you keep recording your time. We record the time in seconds, and it should be recorded to 1 decimal place. So assuming I used 40 seconds, that is 40.0 seconds. Now, when the temperature increases for any chemical reaction, it should take a less time because increase in temperature increases the rate of a given reaction. Of course, I hope we can explain that when you increase temperature, you increase the kinetic energy. And when the kinetic energy increases, the molecules collide more frequently, which increases the rate of reaction. So it means that when I increase the temperature, my time should be reducing. I hope we are together. So probably here, I'll take 35.0. The next one could be maybe 24.0. So the time is supposed to be reducing as the temperature increases. Now, after that, what do we know about these practicals? They can tell you to also work out a figure that we call 1/T, meaning that you're going to divide your time, you divide 1 throughout the time. For example, you get 40, 1 out of 40, and you record your figure. We encourage that these figures are recorded to about 3 decimal places, depending on how many that you have. But you work out the 1/T. Now, when you work out 1/T, the next important aspect about questions of rate of reaction, they will tell you to plot a graph. I said the factors that we are looking at can be temperature, can be concentration. I just talked about temperature here. So which graphs are you expected to plot? They can tell you to plot a graph of temperature against time. And we have just said that when your temperature is high, you'll take less time. When your temperature is low, you'll take more time. I hope from that, we can note that you'll get a graph of that kind, and it's supposed to be a curve, which means that when my temperature is high, I take little time. When my temperature is low, I take more time. And the more time you take, that shows that your reaction is slow. So as we prepare for the practical, please look at rates of reaction. I know it's a topic that we cover in theory, but we also do in practical. Look at how do you determine rate of reaction at a given time. So for example, after plotting this, they can tell you determine the rate of reaction at time X here. What will you do? We expect that you draw a tangent at that point, and then you determine the gradient. When you determine the gradient of that point, you'll have the rate of reaction at any time that you have been asked. That is when you plot a graph of temperature against time. Now, sometimes we can be required. Remember I told you that we also do 1/T. So they can tell you to plot a graph of 1/T against temperature. Please take note that 1/T is directly proportional to the rate of reaction. And at the beginning, I said that when the temperature increases, the rate of the reaction will increase. So when I'm plotting a graph of 1/T against temperature, I should get a straight line. Now you might ask me, what if my points are not in a straight line? Please take note, we draw a line of best fit. We draw a line of best fit. So assuming my point is here, another one is here, I should make sure that this line here, at least some points are lying on that line of best fit. That is when you're told to plot 1/T against temperature. It should be a straight line. Why a straight line? I said 1/T is directly proportional to the rate of reaction. And we said that when the rate of reaction increases, when the temperature increases, the rate of the reaction must increase. That's why we have a straight line. Now, I will not go through the data of concentration and then time because it is the same. If you're told to plot a graph, after doing your experiment, you have recorded the figures, then they say plot a graph. This time you're plotting a graph of concentration. And you're looking at the time. Concentration of reactants. You need to take note that the reactants are usually two. Like I said, magnesium ribbon reacting with sulfuric acid. You can't consider both of them at the time. You can only look at one. So for example, we can vary the concentration of sulfuric acid. You say, that is why for concentration, we usually use something like volume instead of the actual concentration. They can say you start with 20 centimeters cubed of acid. The next one you do 30 centimeters cubed. Then you do 40 centimeters cubed and so on. That is varying the volume. When you vary the volume, you are actually varying the concentration as well. When I use a smaller volume, it means I have used a low concentration of the substance that I'm looking at. If I use a higher volume, it means I'm using a high concentration. Now, after varying the concentration, you still record the time. time taken. That is why we should know how to use a stop clock or something that will help you record the time. And we said the time should be recorded in seconds. So if I get a minute, for example, I should be able to convert a minute to seconds, because we know 1 minute should be equivalent to 60 seconds. So you convert the time to seconds. You record your time, then after that, they tell you plot a graph. Because rates of reaction, we cannot do away with plotting graphs. We have to plot a graph. Now, when you plot a graph of concentration, which I have said in this case, the concentration is given in volume. So assuming we are using volume of acid, and here we are looking at the time. The smaller the volume, the more time you're going to take. So that means we'll still have a graph of that format. And it should also be a curve when you have time and then volume. I said volume here is representing concentration. If I use 20, I'll take more time. If I use 30, I'll take less time. If I use 50, I'll be taking less time. So that is why you see that the smaller the volume, the more time taken. And then the bigger the volume of the acid, the less time that you take. That is if you're told to do this plot. Like I said earlier, they can also tell you to plot 1 over T against the volume. This one should also be a straight line. Why? When the concentration increases, the rate of the reaction increases. And I said 1 over T is a representation of the rate of reaction. So when the volume increases, I expect the rate of the reaction to increase. So I should have a straight line. I should also add, if your points don't give you a straight line, you draw a line of best fit. I beg to stop there for rates of reaction and talk about the last possible number 1, heat changes, or what we call enthalpy change. So this is also another question that can come for number 1. Some of us are only used to titration. We can also have this. But even here, you're dealing with volumes and a few calculations like we did. Even here, we must plot a graph somehow. Now, what are you doing here? You must be using a thermometer. The thermometer is going to measure the temperature change. The common enthalpy that we deal with is enthalpy of neutralization. And we said neutralization, you have an acid reacting with a base. Now these two, as they react, of course they give you a salt and water. But enthalpy change means that when a chemical reaction is happening, heat change must happen. And how do we measure heat change? By measuring the change in temperature. So you record your initial. Assuming they have told me to transfer a certain volume of the acid into the conical flask, they tell me record your initial temperature. After recording that one, I'll add, so assuming this is base, and here I've already put the acid. You must have a thermometer inside there. When you add the two, they will react, and as they react, the temperature inside there will change. Either it will increase or it will drop. But for neutralization, usually the temperature increases. So where are your eyes supposed to be? We are used to seeing the color of the indicator changing. In heat or enthalpy change practicals, your eyes are supposed to be on that thermometer. You see that I started at 25. Now my temperature is increasing 15, 25, it goes to 30, it goes to 40. What do they tell you? Record the highest temperature reached in the experiment. So your eyes are not on the solution, your eyes are on the thermometer to see how the temperature is changing. Now, we'll also have a table to fill. I can briefly talk about the table because I know some of us have been able to see some of these things. So what is in the table? The table, you have volume, maybe of acid or alkali, depending on what you're using, which is varied. Let's say you start at 10, 20, 40, 50, and maybe 60. That is the volume of the acid that you're using in centimeters cubed. The next thing that you're going to record is the temperature rise. When I added my acid to the alkali or the base in this case, now when the volume of the acid is the one being varied, it means that the one of the base is going to be constant, assuming throughout you're using 10 centimeters cubed of the base. So when I add 10 to the 10 of the base, I record the temperature. How far will it go? Assuming my temperature is at 26. I wrote this table because I want to emphasize how we fill the table here. The temperature should be recorded to 1 decimal place. So it is 26.0. That is how we record temperature. Now, I'll do the same, get 20, add to 10, assuming this time I have 34. It should also be to 1 decimal place. So you do that for all the volumes that you're supposed to do. Then, you can also be required to do what we call temperature change or delta T. How do we get this one? I must have got what we call the initial temperature. This initial temperature can be for both of them. I get the one for the acid, get the one for the alkali, and then work out the average. That is supposed to be your initial. Before you mix the two, at what temperature were they? That is the initial temperature. And because I'm using both of them, I divide their temperature to get the average initial temperature. So assuming I started at 25.5 degrees Celsius for my initial, how do I get the temperature change? I'll be subtracting. It means I have 26 minus 25.0. Sorry, 25.5, and that will give me 0.5. I do the same for this one. So assuming this is 40, this is 32, and this is maybe 20.0. There's a reason why I've distributed the figures like that. They first increase and then later on decrease. That is what we expect. The temperature first of all increases with volume, and then later on it decreases with increase in volume. So that is why you see I started with 26, 34, 40, then it goes back to 32. So it increases and then reduces. So to get the temperature change, I have said you subtract. So we'll be subtracting here 34 minus the other one. And that should also give us a figure that we have. So you keep doing that for all of them. Now, the reason I am looking at this, I said after getting this data, what is important for you to remember, decimal place temperature is filled to 1 decimal place when you're feeding this table. And then number 2, when I'm doing an experiment on an enthalpy of neutralization, usually it increases and then later on it decreases. So you'll be expected to plot a graph. Let me talk about plotting a graph here, because you use the graph to determine the volume used. So we'll have volume of acid. And then here we have temperature rise. And they're expected to plot a graph. Like I said, usually if you see the figures of temperature rise don't start from 0. So you might find that my lowest figure is 25, maybe 26, and so on. So I don't have to start from 0. And when I plot a graph, I should have something like that. Increase and then decrease. Then using this graph, I can be required to determine the volume of acid that was required to react with the base that I was using. How do we get it? We usually look at the peak and then read off the volume. Now that volume that you get, you're going to go through the normal calculations. They can still ask you find molarity of the acid, find number of moles of this that reacted, find concentration, calculate percentage purity, and so on. So it is somehow similar to volumetric analysis after this point. Of course, volumetric analysis, we don't, when you're doing titrations, we don't do graph plotting. But in enthalpy, we plot, and rates of reaction, we are also expected to plot. Now, there are cases where I get 2 points that are similar at the peak. So assuming I have a point here, and I have another point there, and I have something like that, how do I get the maximum volume? Because that is what you're looking for. The maximum volume is what is required, the one that gives you the highest temperature. Now that you have 2, we expect you to extrapolate. You draw a tangent there, usually use dotted lines. Draw another tangent there, where your 2 points meet. That is what you use to read off the volume used. So basically that is it about this question. You should know how to use a thermometer, read off the temperature. It is not very easy because you're expecting to see color changes. Here the solutions are both colorless, and the only change that you'll see is the increase in temperature. So your eyes should be very fixed on that thermometer. And then as you record to 1 decimal place. Sometimes they can tell you, instead of using temperature rise, they can tell you to plot change in temperature. Even when we plot change in temperature, the graph will be like this, increase and then decrease. For you to use this, you look at the maximum. Where do I get the highest temperature rise, or where do I get the highest temperature change? That is what you're supposed to use to get the volume of the acid used or the volume of the base. It will depend on what the practical says. After getting this volume, the other questions are the same questions as you receive for mole concept. They can tell you calculate molarity, calculate concentration in grams per liter, calculate percentage purity, calculate mole ratio, and all that. So that is what our number 1 can be. I said it can be the normal titration, it can be rates of reaction, it can be temperature changes, or what we call enthalpy change. I'll talk about question 2 in the next few minutes that we still have. Question 2, you're looking at the ions. We want you to find the cations present, and we also want you to find the anions present. Cations are the ones which are positive, then anions are negative. Your duty is to find out, because they'll tell you you're provided with salt X. What do I do with salt X? It contains 2 cations and 1 anion. Identify the cation, identify the anion. So your duty is to find out if the cations are 2, can I have them at the end of the practical? If the anion is 1, can I have it at the end of the practical? The things that we should take note of here. Number 1 should be appearance. Appearance, you're looking at the color, and you're also looking at the state. They have given me this solid. What is its color? It is white. What is its color? It is green. Number 2, okay, state, I've already talked about it. State. We basically have solids. I have a powder. So I have a crystalline solid. I have a powdered solid. 1, when I see the color, I should know what do I expect. Colors talk about the expected cations, while the state can give me a clue on whether the salt contains water or it doesn't contain any water. If it is a powder, I don't think about water. But when it is crystalline, then I should think about water. That is the appearance of the substance. Maybe I can briefly talk about the colors. When this sample is white, what should you think about? The few cations that you should think about. Probably they are not very few. You have aluminium, you have zinc, there is lead, you have the ammonium ion, you have calcium ions, and then magnesium ions. Those are the ones that we are expected to consider at all level, the white ones. Don't talk about sodium, don't talk about potassium, because we don't test for them at all level. Then, if my sample is blue, this one should be very clear, expecting copper ions. If my sample is yellow, I'm expecting iron 3. If your sample is green, hope you can see here, green is iron 2. Sometimes it can also be copper. Now, these are some of the things that happen when you go to the hospital. They call these ones preliminary tests. The doctor will tell you, how do you feel? Can I look at your eyes? Let me see your tongue. Before they do anything, what do they see? This is a preliminary test. Sometimes the practical paper may not have where they are telling you, take note of the appearance. But even when they don't tell you, that is your duty to look at that sample. What is its color? When I see the color, I should think about what do I expect, and therefore eliminate what is not expected. If my sample is white, I should eliminate the copper, eliminate the iron 2 and iron 3, because for them they are colored. Then I start to concentrate on this list of the white ones. That is what it means. Just like the doctor will say, now the eyes are yellow, probably they are suffering from this. Or they have this, maybe they are suffering from this. That is what a preliminary test is about. Then, later on, they can say, maybe go and they test for malaria because of what they have seen. Or go and they test for typhoid because of what they have seen and probably what you have told them. So even when I look at the sample, that is what I should be thinking about right away. Okay. The other bit is heating is also a common thing that you'll be told. Heat a spatula endful of this sample that you have received. What should you consider? One, there is a gas given off in most cases when you heat. So look at the gas. Number two, there is water of crystallization that you should see. And then number three, you have a residue. Those are things that you should consider when you're dealing with heating. Usually water comes off first if it is present. Orderliness is important when you're doing a practical. So if they tell me to have a spatula end full of the solid and I am heating, I have told you number one, you saw it was crystalline. Suspect water and therefore look for it. Is it given off? Usually it comes off in form of water vapor, and on the cooler side where the heat is not too much, it condenses back to water. So they expect you to talk about a colorless condensate. Now, in practicals, we talk about confirmatory tests. Because you'll make a conclusion at the end of the day that this colorless condensate was water. Then my question would be, how did you know it was water? That is doing a confirmatory test. So when I see this colorless condensate formed, we know how we test for water. We either use copper 2 sulfate, which is anhydrous, or you can use cobalt 2 chloride, which is also anhydrous. What happens when you put it on this liquid? If it is copper 2 sulfate, it should turn from white to blue. That should be part of your observation, that I have seen a colorless condensate that turns anhydrous copper 2 sulfate blue. Therefore, I will go to the column of conclusion. The liquid is water. Therefore, my salt was hydrated. That is water first. I said orderliness is important. Now, when the water comes off, the next thing that will come off will be a gas. This gas has a color. Even when it is colorless, you take note that a colorless gas is given off. Number two, if it has a color, you talk about it. For example, nitrogen dioxide is reddish brown. You can say reddish brown gas given off. Number two, we test these gases using litmus, for you to know whether it is acidic, neutral, and so on. So it is a colorless gas that turned blue litmus paper red. Or it is a colorless gas and it turned red litmus paper blue. Number three, about the gas, is the confirmatory test. I'm very sure that as you went through the practicals that you have done, they will tell you, provided with substance X, it contains 2 cations and 1 anion. Identify the cations and anions in X. Identify any gases given off. No one will tell you now the gas needs litmus. You should know that I should identify the gas by using litmus and a confirmatory test. We don't have very many gases that need a confirmatory test. And I'm sure it is not as complicated as you might think. So they are basically, there's carbon dioxide. That's the other gas that we need a test. Another one is sulfur dioxide. And I'm sure by now you should be knowing how we test for carbon dioxide. We use lime water, which turns milky if the gas is carbon dioxide. Then sulfur dioxide, we use acidified potassium dichromate solution, which should turn from orange to green. These are the most common gases that have confirmatory tests that will be required in the practical. But I said, if the solid that you're heating is a nitrate, it can give off nitrogen dioxide. Nitrogen dioxide has a very peculiar color that is not common to the others. Therefore, you don't need to do any other confirmatory test apart from telling us you've seen a reddish brown gas that turned the litmus paper from blue to red. So, gas, what is the color of the gas? What is the effect of litmus on litmus paper? What is the confirmatory test if I must confirm the gas? Those are things that we should note about the gas. Now, these gases, they tell you about the anion in the salt. If I get carbon dioxide, that must be a carbonate. Because from your theory, you must have known that when carbonates are heated, some of them decompose and they give off carbon dioxide. When I see sulfur dioxide, that is what? A sulfate that I'm expecting. When I see nitrogen dioxide, that is a nitrate that I'm expecting. So gases direct you to the anion that you're expecting in here. Of course, the other gas that I have not talked about, which also has a peculiar test, is ammonia gas. Ammonia gas is colorless, but it is the only gas that will turn the litmus paper from red to blue. It is the only alkaline gas that we do at this level. Now, this one also talks about a radical, but this time the radical has a positive charge, which is the ammonium ion. So the gases should tell you about the ions that you are expecting, especially the negative ones. The only positive that it tells is ammonium ion if you get ammonia gas. Okay. The other bit I said about heating is residue. What is the color of the residue formed? The colors talk about cations present. If my residue is reddish brown when it is hot and it becomes yellow on cooling or when cold, that is supposed to be lead to oxide. Now, of course, that already gives me a clue that the cation I'm expecting should be lead to ions. Please take note that when we are doing the practicals, our conclusions are given by writing proper chemical symbols. Proper chemical symbols. Can you practice writing them properly? If I'm writing lead, I don't expect someone to write something like that. This is a small p, yet it should be a capital P. You're writing copper, and then you're joining the C and the U. The two letters should be separate. So practice writing proper symbols. And these ions are charged. They are either positive or negative. So I don't expect someone to have a conclusion with just copper, metal, because you don't expect metals here. You're dealing with cations and anions, so they must have charges. Copper 2 ions, aluminium ions with a charge of 3 positive. This positive should be written properly. Some of you write it like that, and it appears as a capital T, because I'm not seeing the extension above. Another one will write it and bend even, which is 3T, not 3 positive. Please practice writing the symbols well. That can improve our scores on the practical mark. I think that is it about heating. Like I emphasized there in number 1, that filling the table has very many marks. When we are doing number 2, heating has very many marks. The question could be marked out of 25. And out of 25, between 5 and 7 marks are on heating. So you need to make sure that you do proper heating. When I'm heating, I should look at the gas, look at the residue, look at any water given off, and make proper conclusions. Maybe I can talk about filtration. Maybe before filtration, there's dissolving. They will tell you to dissolve your solid in either water or acid, depending on what you're dissolving in. If they tell you to dissolve in water, that means the substance is soluble in water. Then if they say dissolve in the acid, most likely it doesn't dissolve in water. Now, when you dissolve in the acid, your eyes should be looking out for effervescence, first of all. Because here, it is supposed to be carbonates. Many carbonates don't dissolve in water. Even oxides don't dissolve in water. But mainly, it is carbonates. So why am I saying look out for effervescence? If you dissolve the compound in an acid and you see effervescence, that must be a carbonate. What is your next step? Look for lime water and test for that gas. And that is how we confirm a carbonate. If you look through the paper and it had a carbonate, else it had a carbonate, you'll not find any other question about the radical after adding the acid, because the carbonate will have been removed on adding acid. So anytime they tell you add the acid, first look at effervescence, or are there any bubbles coming off? If there are bubbles, just know you're dealing with a carbonate. Now remember, at the appearance, I said you have a powder. A powder is also indicating that probably there is a carbonate. So if you add the acid and you see bubbles, already that is confirming that you have a carbonate. Now, sometimes we add water and they tell us to filter. What does that mean? I have two solids. One is soluble and another one is insoluble. That is why they are telling me carry out filtration, so that I can separate them. Deal with the residue, because they will tell you keep the residue, and also deal with the filtrate. Filtrate. So you deal with both of them. I've said when they tell you filter, it means one is soluble, which will be in the filtrate, and then another one will be in the residue. So you deal with them separately and identify cations and anions at the end of the day. Maybe one of the things that is now very common that I need to talk about is when you dissolve in water or dissolve in the acid, then after you have done that, you don't filter at that point, but they tell you add sodium hydroxide solution and then filter. Then after that, they tell you acidify your solution. Those are some of the challenging things about number 2, but we can get used to it. So when they tell you to add sodium hydroxide and filter. It means you should be looking at the ions that dissolve in sodium hydroxide and then those that don't dissolve. Usually here, your filtrate is going to be colorless when you have used sodium hydroxide. So it means I will get a colorless filtrate. If this filtrate is colorless and I have used sodium hydroxide, there are not many ions that are soluble. People summarize them as ZAP. I have zinc, aluminium, and then lead. Those are the 2 ions that I would expect in a filtrate when I filter using sodium hydroxide. Now, after that, they will tell you to acidify. Acidifying is a challenging bit, but we should be able to do it. We encourage that you add the acid drop by drop, and you see, because as you add the acid, you'll get a white precipitate. Add more acid, a white precipitate. How do you know that my solution is just acidic? When that precipitate dissolves, you know that now my solution is just acidic. When you have acidified properly, you'll make proper observations. But if after acidifying, you start seeing no observable change, you need to go back and acidify properly. If you add too much acid, you'll see no observable change. If you add too little acid, you'll see no observable change. So you need to be careful as you add the acid. Am I seeing the white precipitate? You keep adding little at a time. Many times we are not patient. And when you're not patient, you'll come and just pour the acid. That means you're adding too much, and therefore the other tests will give you no observable change. So on this bit, we need to exercise that virtue of being patient, little at a time, until when your solution is just acidic, and you know it is just acidic when that white precipitate dissolves. The other bits are the confirmatory tests of ions. I don't know if there's anything else that I need to add here, but confirmatory tests. You should know, how do you confirm zinc? How do you confirm aluminium? How do you confirm lead? How do you confirm copper ions? How do you confirm iron 2? How do you confirm iron 3? Those are some of the common ions that we have. Some of them are confirmed using ammonia. They will give you brown precipitate for iron 3, blue precipitate for copper insoluble, soluble if you're using ammonia. So you should know the confirmatory tests of the ions as well as the anions. The anions expected are also not very many. Probably I didn't mention that. You should know how to test for a carbonate, test for a sulfate, test for a nitrate, test for a chloride. These are some of the common anions that we deal with. You might find some uncommon ones like iodide, but that one is beyond all level, though sometime it appeared. These are the common ones. You should know, how do you test for a chloride? How do you test for a carbonate? Confirmatory tests. Because in the practical, they will tell you, using portion number 5, carry out your own test to confirm the anion present. So if they tell you carry out your own test and you don't know how they test for a sulfate, that means you won't do that test. And you should remember that the question has those 3 portions. You have the test, you have the observation, and then you have the conclusion or deduction. So when they have told you carry out your own test, you must tell us, what have I done? So I have added, for example, barium nitrate solution and dilute nitric acid. If you don't tell us what you have done, yet they have told you do your own test, even if you put the observation that is expected, put the deduction that is expected, you don't expect a mark there because you have not told us what you have done. We are asking you, what did you do? So if they have told you do your own test, you should know that if I'm testing for a sulfate, I should add barium nitrate solution followed by dilute nitric acid. When I did that, I observed a white precipitate. Therefore, I conclude that a sulfate is confirmed. So that is why I'm saying for number 2, take your time to know the confirmatory tests of some of these common ions. If they tell me, test for lead, how do you test for lead? You're expecting that your solution has lead 2 ions. How do you confirm their presence? So I think those are some of the things that we need to take note of. So allow me, probably you'll have a few questions that will be handled by Teacher Eva. But those are some of the things that I can summarize for the practical. You need to do a lot of practice and a few observations here.
Thank you, Teacher Silverine. I see a hand up. Okay, we are going to take very few questions. We don't have much time. I hope we can handle them all. Yes, star SS. Star SS, you can unmute.
Madam.
Yes, please.
I had a question about the letter for chlorine. The way they put it, symbol. The way they present the symbol.
Okay, we have a question on the symbols, the symbol for chlorine.
Yes.
Okay, we'll handle that. I will say something small about symbols. Okay, symbols are very important when we are writing our chemistry exam, as you have been told by all your teachers. So I'll just point out that the symbol, when the symbol is of two letters, the first letter is a capital letter and the second letter must be small. That goes for all the elements that you're dealing with. Now for chlorine, the capital C has never been a problem for many students. But when it comes to the L, I want you to have peace with yourself. This L is correct, the one which is a stick. Even the L which curves a little bit is very correct. The one which is wrong is the L with corners. The moment the L has a corner, it means you now are dealing in a capital L. So that is what you should be mindful about. Otherwise, in some fonts, the stick is what appears as the L. So don't be stressed. Of course, there are other letters which have capital and small, like U in copper. That's an area where candidates lose marks. Copper should therefore be a capital C, which is a big letter, and then the U is small. If you aim at showing it small, even if you forgot the convention, because I think capital U doesn't have that stick, but you make sure your letter is small. So let us watch out about such things. The F, you can make it without design. Generally, don't do designs in the chemistry exam. Then also maybe a common error is we join letters and then the symbol changes. Common here is the symbol for chlorine, where a candidate, because they are in a hurry, writes that. Yes, the L does not have any sharp corner, but they have joined it with a C. So the person who is going to look at your work is wondering whether this letter is a U, a C, or what. So that is what I can say about the symbols. If it's O, let us see the capital O. This is carbon monoxide. Capital N, capital O, and so on. Avoid making these letters small. So my advice to you all students, if the letter is a capital letter, let it be big. If it is a small letter, let it be small. Can we have another, do we have another question?
Yes. Do you get an extra mark for balancing?
I have another hand from, which school is? Kasese Muslim, you can ask your question. There is a question on whether we get any extra marks for balancing. Now, when marking in chemistry, and that is in both practical and theory, if I write the equation, carbon reacts with oxygen to produce carbon dioxide, I must balance the equation. That is what earns me marks. So after seeing that the number of atoms before the equation, before the arrow is equal to those after the arrow, only then will I get the 1 mark. You score nothing for an unbalanced equation. The other mark you will get definitely will be for including the correct states. But you only get the mark for the correct states after you have balanced the equation correctly, and so you get 1.5. So if a candidate wrote out an equation like this, and unfortunately, for example, had a 2 here, this equation is bringing the wrong formula of oxygen. So although the states are correct, the candidate gets nothing because the equation was not balanced. So balancing equations is very, very important in chemistry. Okay, I'll have another question. I think which school is this? Pakacha Seed, you can unmute.
Okay, I have one question, because sometimes the advisors that we should always start with the part 2 minus eating. Now, how can we confirm nitrate while dissolving? Because sometimes we get problem. So that was the only question I have.
Someone has asked about confirming a nitrate. The nitrate, once you have dissolved it in water and you want to confirm it, you'll have to do what we call the brown ring test. And in the brown ring test, it means I'll get the expected solution that I have, maybe solution X. Then I need to add an acid, and the acid added is concentrated sulfuric acid. Then after that, you add iron 2 sulfate. When you add the 2 solutions, you'll see a brown ring forming here. Now, because the acid is concentrated, it is not very safe for students to use. So it is not something that is common for UNEB to set that we confirm a nitrate using a concentrated acid. That is why probably you have been told that we mainly confirm the nitrate on heating. Because when you heat a nitrate, it will give off reddish brown fumes, and it is only nitrates that do that. So we mainly confirm the nitrate on heating, but if you must do a test on the solution, then you carry out what we call the brown ring test, where you use concentrated sulfuric acid followed by a solution of iron 2 sulfate that should be freshly prepared, and you see a brown ring. Paul, please ask your question. Paul, you can unmute and ask your question.
Yes, Yes. I'm grateful to give you this question. That's always disturb us. That if there's a process that needs you to write two equations for different steps, but you've integrated those equations and you have written one, are you also going to get the same marks as someone who have written the two equations? That's the question. Thank you.
Okay. That's a question, I think, in paper 2. I think in paper 3, we don't have occasions where we have to write two equations. Now, oftentimes we are told the instruction is write equation for the reaction taking place. Now, in chemistry, each equation usually takes 1.5 marks. So in most cases, if it is 1.5 marks, then you expect that you're going to write one equation. But sometimes you see there are 3 marks for those reactions that have steps. I will say this, as long as the 2 equations you are writing exist in one of the common textbooks, and the most common textbooks that we are expected to refer to are Certificate Chemistry by Lambert, or I think New Certificate Chemistry by Atkinson. If you have the equations written there in the book, it's okay. What do I mean? Sometimes they could write 3 marks, and that reaction actually has 2 equations. Now, if it has 2 equations, and in one of those textbooks, they have actually written the 2 equations, the 2 of them, then the 3 marks will be awarded, first 1.5 for one, and then 1.5 for the other. But it is possible to find in the alternative book that reaction has been written as 1 equation. Usually in the marking, this 1 equation will take all the 3 marks. So I encourage you to use the textbooks as much as possible. Do not create your own equations in the mind just because you think that sometimes there should be 2 equations. If they are documented, even if you write 1 correct equation, you will earn your 3 marks, okay? We are running out of time. St. Mary Assumpta.
Oh,
excuse me, madam. Madam has another question. That is, assuming the volume used for calculation it's 2I, and that volume is the one you have again used for calculations, will you be treated again badly, like you not be given marks for others who has put it correctly? I think that is it.
Oh. Now, from that question, if someone has got the accurate mark expected in the practical, of course, they will get their marks if they have calculated well. Now, the one who has not got the accurate volume will get some marks, but they will lose some marks, especially on the final answer that I expect. For example, they say calculate the moles in the volume used. And for you, you had 25.0, yet we expected 24. That means we'll keep marking your working up to when you get to the final answer and you lose some marks. So you don't lose all, but you don't get all if you don't have the accurate volume. I don't know if teacher Eva is receiving any other question. Mutesa, Sila, you seem not to have asked. Can you ask?
I was asking that when they say that suggest reasons for the process used in the extraction of sodium and iron metal, what can you say? And another question, if they ask you to give reasons why calcium chloride is added to the ore of sodium, I only know one, which is like when you had calcium chloride, you lower the melting point of sodium chloride. And I was asking for the other reasons for the addition of calcium chloride.
Sorry, we are having issues with our connectivity. Yes, there are other reasons, though the most obvious reason, and which is the one which is commonly asked, is that one, and which the answer you will find that the reason is to lower the melting point. But the other one is also, I think when you put calcium chloride in the melt of sodium chloride, it affects the solubility of the sodium, I think at the time of collection. So that is what you should look at. But the most common is lowering the melting point. Now, my dear learners, let me say this. Can you take time and read your chemistry work? You have the textbooks. Chemistry is one subject that has little content. Take time and read that content, because what you study in senior 1 and 2 is repeated in senior 3 and 4. Do not ignore your senior 1 and 2 work, read it. Then also an area students ignore, which is very easy, is applied chemistry. Applied chemistry has answers which usually do not require equations. So do not leave that beer making. I think there are very few, very easy marks to get there. There is hard water. Can you read that hard water? Hard and soft water. Water treatment. Those are things we should read, and we read them and hope that we will be asked about them. We can talk about soap. We can talk about, what else? What other applied? The extraction of metals is a form of applied chemistry. Is a form of applied chemistry which has equations. But if you're good at equations, do it. Otherwise, most of this, there's not much equations. Polymers is also very easy. I hope you can read it. Polymers is related to the fibers. Please read about the fibers. The sugar is also there. Please read all that applied chemistry, and I'm sure you'll be able to move on. Unfortunately, it seems our time is running out, but I am going to just let Teacher Silverine handle the 2 questions I'm seeing in the chat. Those whose hands are raised, we are sorry we can't handle you, but let's handle the 2 which I'm seeing in the chat, and then we call it a day because our time is spent.
Emphasize acidify, then in titration, can you also choose the 2 smallest values?
Now, of course, if you're saying that 2 smallest value, that is handling the last question on titration. If you're choosing the smallest values, I said you need to consider consistency. When I subtract the 2, they should give me 0. If they don't give me 0, then they should give me 0.1. If that is the difference between the 2 figures, there's no problem choosing them. But I can't say choose the smallest figure. Your question should be, how, if they are the smallest, are they consistent? If I subtract them, what is the difference between the two figures that I am subtracting? If they give you 0, assuming they are the smallest, and you have 14.00, then the other one is also 14.00, it means that 2 are the most consistent. If one is maybe 14.9, not 9, 14.10, this is also still consistent, so I can use them to calculate my average. Lastly, emphasizing acidifying. That is something that needs practice. I talked about patience, which you need. I have prepared my solution and I have used sodium hydroxide. It means that this solution here is alkaline because it has got excess sodium hydroxide. Because they tell you, you add excess such that the one which is soluble will dissolve and you get it as a solution, and then the insoluble one, you'll get it as a precipitate. So you tend to use a lot of sodium hydroxide. Now, when they tell you acidify, what are you doing? You're adding the acid, which is probably nitric acid because it is the common acid that we use. I said add drop by drop. As soon as you add, you'll see a white precipitate formed. Now, this precipitate is expected to dissolve. That is when you know that my solution is just acidic. Now, if you simply pour the acid, it means you may not see the precipitate and you have added too much acid. It means whatever you're going to do next will give you no observable change. So what I can only say here, try to practice adding 1 drop at a time and you see that precipitate. If you don't see it, do it again. You can prepare enough solution and you keep adding until you see the white precipitate. Then if the precipitate dissolves, it means your solution is just acidic. We can talk about using litmus paper, but that is something that we don't recommend. That can also help you to know that your solution is just acidic. When you add the litmus, because there's too much alkali, it will be blue. When it becomes acidic, that litmus paper should turn red. If it is challenging you to see the precipitate, you can use the litmus paper. But the expected observation on acidifying is white precipitate that dissolves in the acid. The litmus paper is only helping you to make sure that you know that my solution is just acidic. The word is just. It means as soon as that precipitate dissolves, you should stop adding the acid. I think that is it from me, Teacher Eva.
Sorry, Teacher Silverine, let's hear one question from the last school. Nyangira SS Koboko, please ask your question. You can unmute and then we will wind up with that.
Thank you so much for the presentation. And like to know that there will be another program that you can communicate before you go off air.
Pardon, could you be a little clearer? I can't hear the question.
Thank you, madam. Hello?
Yes, I can hear you.
I was saying, since it is the first time program, may I know whether there will be another one so that we can prepare for it?
Okay, I think Mr. Kaziva can help us and answer that question. Mr. Kaziva, could you help them and inform them about the program from HELP?
Okay, thank you so much, Teacher Eva. We are going to sit down this evening and then think about on the next steps. It is really unfortunate that UNEB is starting. Some schools I think have already started. So we don't want to contradict with what your neighbor has already set out, but we are going to let you know whether we shall have more other sessions before the week for briefing. Yeah, but we are preparing in case of any chance, we shall have biology, but we are yet to let you know when we shall have biology. But if things go on well, we shall have it next Friday at around 2. Yes, but we are going to let you know using the different platforms whether we shall have that session next week. Okay, thank you so much. I want to extend my sincere appreciation to teacher Eva and teacher Livia for the wonderful session and for taking us through this session. Teacher Eva and teacher Sliverin, we are really very grateful and thank you so much for accepting to take us through the chemistry papers this afternoon. Thank you so much. I want also to thank other schools that have connected in from the different parts of the country. We are really very grateful and thank you so much for accepting our invitation. We want also to thank all the teachers that have connected online and that have been able to connect their teachers. I've seen some head teachers from West Nile and also from Central Uganda. Thank you so much for connecting your students. We are really very grateful. We are supposed to have the principal. We had some ministry officials. Unfortunately, they went off, but they have been also following this session. Also, we want to thank you so much for sparing time to be on this call. We want to thank all the students. I know you may have more questions, but please, you can share those questions. Teacher Eva and Teacher Slivery will be able to take on those questions when time allows, and they can be able to answer in case there is any question that you may wish, or the teachers that there is anything you may need more clarification. Please feel free to reach out to Teacher Eva and Teacher Slivery. They will be able to answer those different questions. I don't know whether Teacher Eva, there is something you want to say with pros and Teacher Silvering, anything for the students, any closing remarks for the students before we leave?
We only want to say that we wish them the best of luck. Please do not give up on chemistry. It is easy to pass it. Just put your last energies into reading it, and you will surely excel at it, because it is lovely to pass chemistry. Even those who don't want to do it at A level, it is okay to pass chemistry and you drop it at A level. We wish you the best of luck. May God bless you.
Okay, thank you so much. I'm going to ask schools that can turn on their cameras. Kindly have your camera on. We want to take one photo that we shall be able to put in our report. So you can turn on your cameras and then we look at those beautiful students. Turn on your cameras. Let me see whether mine can also turn on. You can have your cameras on. So we are going to take a photo together. Okay, so okay, so one more photo. Okay, those who can have your cameras on, such that we can take a photo together. Okay, thank you so much, everyone. We wish you all the best, and let's meet again when we call out for the session. Bye-bye, everyone.